So today we're going to finish up the vulnerabilities, the D9, and then move on to the next part of the class. So I'll do off-chain attacks, take a break, and then I'll start on Viper. So we covered a whole bunch of attacks on the smart contracts themselves up until this point. There is a whole bunch of attacks that happen off the chain, some real deviousness that deals with other parts of the computing system. So one of the interesting things is that this is actually covered in the D9. They only list this thing, but there's a whole bunch of other ones that I threw under this heading because it's more than just this one. Is the short address attack. So what is this? Well, here's the example of how this got, well, it didn't get exploited, but it was identified. It could have been exploited. This person was looking at the code of a popular exchange and realized that there was a bug in it that could wipe the whole thing out. This is an issue with what's known as insecure marshalling. So as we are making function calls from one part of the system to the next, we have to marshal our parameters from one system over to the next. That's what data marshalling is. I mean, we don't really talk a lot about that. Maybe in the database classes you talk about marshalling, but this is similar to, for example, if you're taking the cloud class, marshalling data into JSON and then sending JSON back and forth. You have some data that you want to call maybe in Python, and then that gets marshaled into a JSON object and then sent across to a backend. That's sort of an example of marshalling in computers. So there is some marshalling going on. You have some web API or some web interface to your smart contract that Web3 is interfacing with, and you're taking data from the user, you're packaging it up, and you're creating a transaction that will then go into the blockchain, and it will go into a full node. So that's the marshalling operation that we in particular are going to look at next. Here's a walkthrough example of an exploit. So you have this web API that's taking in two parameters from the user, the address that you want to send some coins to, and then the amount of coins that you want to send. These are the function parameters. And the goal is to eventually call this smart contract. And this is what the smart contract does. It gets the to address, it gets an amount, checks to see if the sender's got the right amount, and then just transfers it to that to address. So this is something that you've seen before. One thing to note is that the way function calls are done is that you take the kekak hash of the function signature, the interface, and then what you do is after this hash, you then list all of the parameters following that, and that gets packaged up into message.data, and that is the thing that you send to the full node, saying, I want to invoke this function with these parameters, and then it goes and it executes the code that's on the blockchain. Okay, so the attack is, so Bob is the attacker in this scenario. He's got a wallet address that ends with a null byte. So he can keep on generating wallet addresses until he finds one after maybe 256 tries. He finds one with a 00 at the end. And then asks Alice to transfer 2 tokens to him, but instead of giving her the actual full address, what he's going to do is truncate this address, and instead of sending a full 20-byte address, we'll send 19 bytes instead. Okay? And we'll see what this does to this transaction. So this is the way it is intended to operate. So Bob, with that wallet address, wants Alice to send him 2 ETH via the sendCoin call, and the sendCoin call has this hash associated with it. So I've color-coded all of this so you can see where this thing goes down. If Bob were not malicious, then he would send through the web form that full 20-byte address and the integer 2, because it's 2 ETH. And then Alice will generate this as message data. So it starts with the hash, and you can actually see this on the blockchain when you pull the transactions down. You can see this exact format. The hash of the function you want to call. The first parameter immediately follows it, which is this 20-byte hash that is padded out to 32 bytes, right? So you're doing some padding to align the data on 32-byte boundaries. So that's what happens. So that's what this says. It's always padded out to 32 bytes. And the UI always assumes that it's going to pad with 12 bytes because who would ever give it anything other than 20 bytes? So it just, hard codes 12 extra bytes onto whatever address is input into the UI. So then the malicious Bob sends instead the first address instead of the second. It's got a null byte truncated. And then Alice, using this improper marshalling code, sends the contract this. So again, you gave it 19 bytes plus the 12 bytes of padding. That gives you an extra byte that you basically will borrow from the next argument. So then Alice will send the rest of this. So this is 1 byte short, right? Alice is actually going to send the Ethereum virtual machine a message.data that actually has 1 byte less than the legitimate message that she would have sent. So instead of the one that we saw previously, we get this payload that gets sent to the EVM. So this is a problem because the missing byte of that address is, first of all, it's pulled from the green, and then because the EVM is expecting 2 32-byte arguments, the EVM is going to append this yellow byte of null to the last part of this payload. And so what this does is that this results in Bob receiving 512 ETH instead of just 2. Okay, so that's the short address attack. Is that pretty clear? Pretty devious, but this is where one of the problems is that you're abstracting all of this stuff out to the programmer, and then the programmer really needs to be careful when they're using the underlying blockchain. So remediation, this is every time you take a security class, it's input validation. Never trust untrusted input. And this happens everywhere, from buffer overflows to web injections to this kind of stuff. You always have to check all of the data being provided by the user. And one thing you can do is you can generate the transaction data, and then you can basically cross-correlate it back to what the user data was and make sure that they match as one of the remediations. Only use checksummed addresses. This is why they started checksumming addresses, because an address with that null byte omitted won't pass a checksum. And so this was initially done in band with Bitcoin, and the way they did it with the Bitcoin was to use capital letters for the hex digits, selectively using capital or lowercase. And then this is now done for all Ethereum addresses using the EIP55 standard. If you get an address, you can generate the checksum version of it by going to this ETHSUM link, which I have on the website. The other thing is to always use vetted implementations of Web3.js, for example, that does do the secure marshalling of user addresses into transactions. And then finally, you could also, well, actually not finally, one other thing that they were trying to do was to actually change the EVM to throw an error on data underflows, rather than just implicitly padding the missing byte. You should never, this is sort of like PHP. PHP is like, oh, I think you made an error. I'm going to try and fix it for you, and then move on, rather than just completely fail. You want the thing to just completely fail, actually, is the intended behavior. But a lot of people are like, well, if it completely fails, I'll people won't use my cryptocurrency platform because it's too hard to use. So that's the trade-off. And that's how PHP started running everything, because it never failed, and people are never having to debug at compile time or at programming time. Okay. So this got completely fixed. So we're not doing this. If you use Solidity greater than 0.5, then this is completely fixed in the compiler to do these checks. Of course, we're using 0.4.24, so we're not quite there yet. But basically, as soon as the fix made it into Solidity, now all these short address attack checks are being removed from everyone's code base. But this is just an example of the need to validate all your input. Another class of vulnerabilities is just server vulnerabilities themselves. So the software that is running all of these full nodes is extremely complex. And it's much too large of a code base to formally verify the correctness of. And so you could have a formally verified smart contract, because smart contracts are small enough to formally verify their operation. You could have that thing be completely bulletproof, but because of bugs in the underlying EVM code or the underlying full node code, you could get compromised. So completely correct smart contract, somebody like pulls the rug underneath you that you had depended upon, and then you're compromised. And so this is what happened. We talked about the Verge network, the Verge blockchain being subverted all the time. One of the subverted mechanisms was to take the difficulty of a puzzle and put it down to basically 0.001, and then to DOS all the miners in order to get money. Well, the way they got this thing to go down to 0.0001 was a bug in the mining algorithm implementation. And so that's how, and this is off-chain because it's not within the smart contract itself, is the idea. So remediation, this is why all of the full nodes running are either in Rust or in Go. All of these memory-safe algorithms. If you run into a blockchain that the person has programmed in C, run away as fast as you can, because that blockchain probably isn't secure. So this is why Geth, which is what you'll be running next week, or actually later this week, and then Parity and Lighthouse are the Rust versions of this. This is why people are working on formally specified virtual machines and languages. So Cardano is an academic blockchain that's looking at trying to formally verify all the different pieces of this, so you can then you could trust what's running. So formal verification of the EVM, formal verification of the smart contracts running on the EVM. All of this stuff is stuff that people are working on to try and make this something that you can not subvert. So this is a picture from Cardano's flowchart of what they're trying to do. Another interesting class of attacks are supply chain attacks. So just poison the software being used. So we talked about Web3.js. Who manages that? Who do you like we've got it running. You've been using it, but you have to ask yourself, well, who actually distributes this JavaScript, and what is the reliability of that? Moreover, you're relying on MetaMask, and you're relying on the authors of MetaMask to be trustworthy and to write trustworthy code. And unfortunately, if you are relying on a whole bunch of wallet software and you don't really know who has generated it, you could be open to a supply chain attack. So here's an example from last year. So NPM is the Node.js package repository, and it's got hundreds of thousands of packages that you can use in your JavaScript app. And there's a lot of wallet software in NPM. And so someone figured out that a lot of the Bitcoin wallets were using a specific NPM package, and they masqueraded as a developer, and they tried to get ownership, and they did get ownership of some of the packages used in these wallets, and then they subverted it. So this is what happened to EventStream. So this is one of these libraries that's included in a lot of the implementations of wallets. So 2 million times per week. But it's one of these pieces of dead code. It's there. There's not much going on. It was basically not maintained for a period of 6 years because it was just code that worked, and then people were using it. So the original owner was like, I want to get this off my plate. I didn't know it was being used by a whole bunch of crypto wallets. So there was a volunteer who approached the original owner, says, I'll take care of your load. That's a heavy burden you're carrying. Let me own it. I'm a good Samaritan. And then basically this malicious new owner adds a dependency to some little-known library called FlatMapStream that had no downloads, and then inserted some malicious code in that new package that enables Bitcoins to be stolen. So again, if you're using wallet software that basically is relying on packages where the wallet software people aren't paying attention to where they're getting their software from, this is an issue. And this is becoming increasingly problematic in the way we run software. So the remediation is to monitor and validate your software supply chain. Try and reduce the packages that you depend on. But you end up with a philosophical question is, do you patch or do you not patch your wallet software? And so this is an interesting one because this is similar to the difference between getting infected by WannaCry versus getting infected by something like CCleaner. So WannaCry was this NSA bug that got released, and people just have not patched the dang thing. Like this is a ubiquitous vulnerability, and basically the NSA was using it to great effect to subvert potentially adversaries. But the problem is that nobody was patching. Well, not a lot of people were actually patching the thing. And so we tell people, oh, always patch your software, every day, patch your new software. But then you have this thing called CCleaner, and the way the adversary subverted CCleaner was to get into the supply chain and insert the malicious code in the software patch, and then because people were diligently patching, you got all the first responders. So now you're like, well, what do I do? Like, do I patch aggressively or do I wait? And this is a tension that now we have to deal with trying to secure our software. So increasingly in a pip and npm world, you might not want to patch. And this is the supply chain problem, the software supply chain problem, because it's so massive. I showed you that iceberg. I showed you the iceberg, right? That's the reason why you have to be careful about just updating. Okay, another huge attack vector is attacks on exchanges and what we call hot wallets. So the most famous example of this is Mt. Gox in 2014. So this was a Bitcoin exchange that at the peak was handling more than 70% of all the transactions. And it was handling these transactions in what's known as a hot wallet. And so what happens is you basically give your private keys to Mt. Gox, and it stores them, and then whenever you want to transact, it will unlock those private keys and then use them to submit transactions on the blockchain. Okay, so there was a compromise of their servers in 2011, and this didn't break into the hot wallets. It basically changed the pricing on one of their systems to basically be giving away Bitcoins for a penny. The real compromise happened in 2014, where the adversary obtained the private keys of a whole bunch of Mt. Gox clients. And because these were stored in hot wallets, these private keys were live, meaning that because they were there, they could transact immediately with these keys. They were able to abscond with basically $500 million worth of Bitcoin. And this brought the whole exchange down. So this is actually, yeah, 17 billion worth at 2019 level, so inflation, I guess, or whatever, the bubble. So this has happened in multiple places. So I guess people didn't really, they forgot about Mt. Gox. So here's an exchange coin check. that also had all of their digital assets stored in a hot wallet. And so because they kept it in a hot wallet, as soon as they were compromised, those funds could immediately be wiped out. Okay? Because the keys were basically attached to the internet, and from the internet you could basically use those keys directly. And then the most recent one was Binance. So this was the thing we talked about where the guy wanted to do a reorg on blockchain and then got yelled at, basically. So what happened with them, so they're the 7th largest crypto exchange in May. And what happened is the adversaries were attacking all of the high-value users who were using Binance to do the exchanges. And they absconded with basically 40 million of Bitcoin. And this is actually equivalent to what the DAO, the Ethereum DAO attack netted. And one of the interesting things is that Binance is actually doing some security. They're doing two-factor authentication. They're trying to secure their APIs with access tokens. They're trying to add security into this. But basically, the adversaries are using just the standard security attacks, phishing, viruses, other attacks on the actual users themselves. And because Binance is storing all of their funds in a hot wallet, it basically allowed them to just wipe out a particular user's account as soon as the compromise happened. So these are operational issues dealing with exchanges that lead you to lose all of your money on the blockchain. They're not actually on-chain attacks per se, which is why I'm covering it now. Okay. And so if you had your Bitcoin in Binance's hot wallet, it now belongs to someone else, is the bad news. Okay, so what are some remediations? This is why people are using hardware wallets. So you can force the exchange to require a signature from your hardware wallet that you carry around in order to validate a transaction. But the problem with the hardware wallet is that if you drop your hardware wallet into the toilet, there goes your cryptocurrency too. So that's a single point of failure that people are really nervous about. Another thing you can do is to use hardware tokens, the security tokens, to authenticate the hot wallet. So in this case, for you to do a transaction on Binance, you would have to insert your security key, assuming that Binance didn't support this before they got hacked over the summer. I'm guessing they probably support this now, because the quote from this guy right afterwards was like, the company plans to give away 1,000 YubiKeys when the feature goes live, right, for all of their clients who actually need this kind of security. And then it might make sense for you to actually keep it in a hot wallet for convenience. Okay, so that's another remediation. The other thing that people do is use cold wallet storage. You keep the vast majority of your assets. You keep the private key for ownership of those assets in a bank vault. And then you're basically transacting, and then every once in a while you use the cold key to actually do some large, infrequent transfers. So yeah, keeping these things offline is what most exchanges would do to keep most of their assets locked away. Which is sort of hilarious, is like the cryptocurrency is supposed to replace banks, but then it's using the bank to store the keys to the kingdom. So it's a little ironic, I think. Another one is to use multi-signature wallets. So Bitcoin has this thing natively where in order for you to transfer some money, you have to have multiple signatures. And so if you own all the different signatures, the adversary has to compromise more than just one. So that's an interesting way to do this. Okay. The next one is weak or leaked keys. So we rely on the cryptography being properly used in our wallets to sign signatures or sign transactions in a way that the adversary can't pull any information out of in terms of our private keys. The problem is that if the people writing the software don't understand the underlying crypto algorithm, then they could be doing things that look like they're secure, but actually aren't. So there is a way, if you generate a bunch of digital signatures, if you can get a private key to generate a bunch of digital signatures in an insecure way, there's a cryptanalysis attack that would allow someone to then reveal the private key itself. And that's what this particular attack is. So this is a vulnerability in the way a whole bunch of systems are using the keys to do signatures. And so if you have enough transactions using this weak signature scheme, someone can reproduce your private keys, which is game over on your account. So that's a paper. This was released this year, actually. So it's not earlier this year is this one. Another one is improper key generation. So all of these algorithms for generating your public key, private key pairs, they have to be configured appropriately. Otherwise, you'll end up with keys that are not truly random. And so blockchain.info had this security disclosure. There was a point in time, there's basically 2.5 hours, where they had deployed their wallet generation algorithm with a improperly configured crypto algorithm. And so if anybody generated wallets during this time period, then someone could go in there and just derive the private keys immediately. And so this is where people are suggesting that the flaw still exists in ECDSA, which is sort of the algorithm that most blockchains are using, but it's much worse than RSA, the misconfiguration problem. Okay, another really interesting exploit is to pop up a fake key generation site, advertise it, and then collect everyone's fake keys, and then wait a couple of years until they start using it enough to get assets. And then because you know their keys, you can wipe out their accounts. So this is basically what IOTA was doing. And they basically stole 4 million in assets. So it was 2018. Well, it was running, I think, in 2016. And then basically they absconded with everything in 2018. So this was their site. I think this is from the Wayback Machine because the site was taken down after they realized this. So they had this site where you mouse over the UI and it says that it's collecting randomness from your mouse movements to generate your super secure wallet seed to generate your private keys. And then, of course, it would generate this, which is, you've seen this before with your wallet phrase. And then it would say, oh, this is your super secret private key, copy this, and then use it to generate your keys. And then they just stored this away. And then they waited. And now they have a bunch of keys for them to then go and who knows, maybe MetaMask is doing that for yours. Who knows? You got to make sure nobody's like. How can you tell whether or not someone is doing this? That's basically the issue here. Okay, so it ended up storing the seeds instead of well, it stores the seeds and then it can wipe out your wallet. Here's another example, walletgenerator.net, and it was a little bit sneakier. Well, actually, the previous one's pretty sneaky, but this one's pretty sneaky in that it was using a coding sleight of hand. So the algorithm for generating the private key had basically an intentional backdoor, a crypto backdoor that was very subtle. And so most people looking at this were like, oh, that seems like a legitimate way of generating keys, but not. It actually had this crypto backdoor. And then all of these funds were left open to theft. Okay, and the last one of these is the comedy bug, leaking the private key. So this was caught earlier this year. And this cryptocurrency wallet was caught sending the user passphrases to Google spell checker. So this is pretty, well, I mean, it's not funny for the person who found it because basically he lost 90% of his funds. But this is what was happening. So when you export your wallet, and you'll be doing this in your lab. You'll be exporting your wallet phrase from MetaMask and importing it into Geth. So this person is trying to go from one wallet piece of software to another, is exporting the, he's exporting the wallet's key phrase, and he's trying to restore it on his target wallet, and he's pasting in the words to do the restoration, and the person who implemented this, whether intentionally or not, basically was sending the phrases over to Google to be spell checked. And so this, revealing anything over the network like this, at least it was HTTPS, this thing is basically going to reveal your passphrase. And this is his screenshot saying, hey, this is not cool. Okay. Another class of vulnerabilities involve the network. One of the more common attack vectors is this thing called DNS rebinding. And so when you set up your Geth light node, what Geth does is that it runs a local JSON RPC interface. It's like a local web server that only takes in requests from processes that are on the same machine. So you're going to run Geth. You're going to open up your private keys and your wallet, and then you're going to use web requests, basically, locally on that machine to interact with the blockchain, is what you'll be doing. And so typically, you don't want this web interface to be accessible by everybody, right? Only you on that machine should be able to access this interface. Okay, so the DNS rebinding attack goes like this. The user goes to a malicious site, evil.com, and loads the DNS entry for evil.com. And the DNS entry, the adversary has encoded a very short time to live on this entry so that the name to IP address lookup will time out almost immediately. It's almost as if only the origin request will go to the right domain. And then upon the client, the victim, loading evil.com, what happens is they load the base page, and then all of a sudden they need to go to the embedded objects. And the embedded objects are also at evil.com, but what the adversary does is it immediately switches evil.com to point to the local RPC interface of their wallet. And because you're a web browser, and if you run your wallet or your Geth on the same machine as your web browser, then they can redirect your subsequent loads to your wallet software rather than to evil.com. Okay? And then when the user loads the embedded objects, it's instead redirected to the local interface that's running the wallet software. And then if that interface isn't written to require continual reauthentication per request, then these requests can have access to the complete unlocked keys of the wallet, is the exploit. Okay, and so there were several Ethereum clients that had this vulnerability, and this is why when you run your Geth, it says -- allow insecure insecure wallet access is one of the flags, because then Geth eventually shut the whole thing down. But in order for us to do the lab, we need to open it back up. So hopefully you don't have anything stored on that wallet except for the coarse stuff. And so this is an example of this. You go to this site that's got this malicious site, and then all of a sudden it pops up your Ether account, and it gets access to the balance of your Ether account. So this actually happened with this particular wallet from last year. This is a picture of it. So the first thing that happens is that here is your wallet software, and it's running on the same machine as the user. And then you basically connect up to your wallet, and this is also running on the same machine. You unlock the wallet, and you say, keep this wallet open for 15 minutes. And these two things are running on your computer, the wallet software. And then you visit the adversary. So here's your browser. And you're going to visit evil DNS over here on the right. You resolve the domain, and it's the domain of the evil server. You open the site, and then there's this hidden iframe And this iframe is something that you're going to be forced to load eventually. And so this returns the page in the JavaScript. And this is where the rebind happens, where you say, okay, I'm going to give you a payload. And within this payload are a whole bunch of accesses to to this evil name. But instead of giving you the one that I gave you initially, I'm going to give you your wallet address, or your wallet software address. And that's basically what this does. I'm going to bind the origin back to localhost. So when I resolve it again, it says point to localhost, which is 127.0.0.1. And then this forces these transactions that were encoded in this iframe to hit your wallet address. And you have unlocked your wallet keys for 15 minutes. So then basically you can sign whatever transactions you want out of this wallet and then steal the person's money. Okay? This might be hard if you haven't taken the networking class, but that's what's going on with this attack. Okay, so here is actually a picture from that write-up. So here's where you're unlocking your wallet keys. And then this is putting up a local RPC interface. And then here's where the adversary has this site, and the adversary gets some JavaScript to run that exfiltrates your wallet key. And you see that this thing matches what that thing is, because it's rebinding to your local wallet. Okay, another set of attacks is DNS hijacking. So this happened last year. So MyEther wallet, it's similar to MyCrypto. In fact, we used MyEther wallet last spring, but then MyCrypto basically subsumed its functionality. So MyEther wallet is a really popular site for people to use their wallets, to connect their wallets up to. And basically what happened was that the adversary attacked the AWS DNS servers, because MyEther wallet was using Route 53, which is AWS's DNS service, hosted DNS service. They were using that to serve their names. And so what happened was the adversary got in there and did a BGP hijack of AWS's DNS servers, and then rerouted the DNS requests to MyEther wallet to their own. And then the IP addresses that it got rerouted to, they popped up a fake MyEther wallet site. And in that fake site, they were like, hey, we need your private keys because you've lost your authentication. Enter in your private keys to reestablish your account. And then they were able to phish a whole bunch of accounts that way. And so 150,000 is not much. 216 Ether were known to be stolen, but it's likely higher, because if you look at the wallets that these funds went to, there's about 365,000 in those wallets. So this is actually a very cost-effective attack if you can launch it on people. Okay, another type of attack is phishing users. One interesting one is to spoof the Ethereum address of whoever is receiving Ether. So if a company is modifying or it has advertised their Ethereum address for you to send money to, like if you're doing an ICO, then you can replace that address with something else. So that's what happened with CoinDash. They had an ICO, they had a website saying, hey, if you want to buy into our ICO, this is the contract address. And then basically someone with a basically compromised the website and then changed the address. And so then, and this was after the fact, they were like, hey, don't send that other address any ETH. And of course, $7 million were sent to that address. And so you can actually see, this is the balance of that fake address. And you see a whole bunch of people lost their money doing this. So that's an interesting attack. Yeah.
We've gone over quite a few different times where money has been taken from people. Is there any legal repercussions? Do people get sent to jail for stealing?
Are there any legal repercussions? Not. You have to be able to track down the location of the person who controls those addresses. So yeah, if law enforcement has the tools to be able to identify where the source comes from, then yeah, you can go after people. And this is what's happening in Bitcoin. Law enforcement is getting really good at tracking down, because you can trace all the transactions for a particular wallet, and then the person who owns that wallet has to have really good operational security, because if people see where those requests are coming from over the network, then you might be able to triangulate where the owner of that wallet is, and then you can go and get them. And actually, there are some cases. I don't have the links right now, but there are some really good case studies of law enforcement tracking transactions on the blockchain in order to actually get at the people behind them. But it's not an easy thing.
I mean, like, even if they did get away with it, how would they pull it out of the blockchain?
One of the things, if you compromise a bunch of currency, you can basically redistribute them to a whole bunch of other addresses, and then it becomes a real tracing all of the pilfered currency throughout the blockchain makes it much harder. So you'll see I'm going to talk about anonymous sort of wallets later. But there are these services, and these money laundering services is basically what's being implemented, where you have a mix of a whole bunch of funds. You have a contract that just takes in a whole bunch of money, shuffles it up, and then sends it back out. And in that way, you don't know who are the addresses that are legitimate and who are the addresses that are not legitimate. Because a lot of people want to sort of protect their privacy from law enforcement, and then other people are just trying to hide criminal activity, right? And whether or not that's actually legitimate or illegitimate, this laundering kind of operation is questionable. So basically, law enforcement is now looking at all the contracts that are doing this money laundering operation, and they're going after the money launderers to get rid of that kind of functionality. Well, there's a system called Zcash, or Zero Cash, which is trying to be anonymous from the get-go. And as it turns out, 90% of the transactions going through Zcash are for illegitimate activities. So that's, and then what do? Do you get rid of it to go after the 90%, and then basically the 10% that's legitimate get hosed? So yeah, this would be more of an ethical thing to think about. But those are good questions to ask, actually, in a broader sense. Okay, another thing is straight up spoofing legitimate sites. So blockchain.com is this really useful site for exploring the blockchain using whatever wallets you have. And someone was able to pretend to be blockchain.com and then steal 27 million in cryptocurrency. And so these guys got caught. So because if you're going to do this kind of thing, you have to have really good operational security, because people are keeping track of all the logs, keeping track of all the network traffic. If something like this happens, you can basically do some forensic analysis. So this is what happens when, for example, the DNC gets hacked. We have all of the logs. It's a matter of getting an incident responder, like FireEye, to go in there and then figure out where all the stuff happened. It's like, yeah, you have to go through the network, sort of like a surveillance camera. Once something happens, well, then you go back and you look at the video log of that. We have the same thing with network traffic and computer logs that would then, if the person hasn't done enough to hide their identity, then law enforcement can get right in there and figure that out. And actually, this is a pretty good career for any of you who are interested in this, because the level of technical expertise in government is not as high as you would like. Let me put it that way. Okay, so this is really interesting, because at one point in time, if you did a search on blockchain, this is what the Google AdWords would show up. And if you look at these things, these are definitely typo squatted malicious entities trying to fish the heck out of their users. So that's not legitimate. That's not legitimate. It looks legitimate. And then that one is legitimate. Well, that's not so the adversary is sitting there buying AdWords to show up so that people will click on it. And people do click on it, otherwise this wouldn't actually be here. You wouldn't see this screenshot if people didn't click on it. So here's an example. This looks like blockchain.com. And of course, if you zoom right in, actually I have zoomed it, if you look at the URL bar, you see it's that. So yeah, you know, my geriatric eyes would be like, that looks legit. And then you're like, oh, that's not legit. Like when you zoom that thing up, you're like, oh, that's not quite right. But these things are hard, right? Because you can scrape blockchain.com and get all the assets so it looks legit. And then it's just a matter, and this person actually got a certificate for this. So this is a secure, this is where, did I talk about this here? This is where that green lock is really messing novice users up. Because this is clearly not legitimate but for us, but then this clearly looks legitimate to everyone else because of that visual cue of the green lock. Okay, but that's another class. That's not this class. So some remediation. So interesting enough, password managers is a remediation because password managers, when you register a password, it's bound to the DNS name. And so if something looks like blockchain.org or blockchain.com, your password manager won't give you the automatically fill in the password field. And then you'll be like, that might not, you know, I swear I registered my username and password for it, but your browser or your password manager software will refuse to fill it in because for sure they don't have the password manager can figure that one out. Doesn't need reading glasses for that. Another thing is two-factor authentication on these sites. Again, the hardware keys and these sorts of things. Okay. So that is what I'm going to cover for off-chain attacks. One of the things that I want you to do is do the next lab of 5 points. So there are 2 sections of labs left. Section 4, which I'm going to cover next, and then Section 5, which I'll be covering next week. I want you to go and do the first lab of Section 5. And this is because it requires you to run Geth for a little while to get up to date. So the Manticore setup lab is what I'm going to walk through next. So Manticore is a symbolic execution framework, which I'm going to talk about what symbolic execution is. This is basically a piece of software that allows you to automatically compromise a smart contract. So in order for us to run Manticore, we actually have to run Geth. So this is what the Code Lab is doing. You all have Google Cloud accounts. So what you'll be doing is you'll be creating a virtual machine on Google Cloud. You'll be installing Geth, and then you'll be running it. And that's what the first Code Lab is. Let me know if you somehow ran down your coupon. I can issue you another one. So you're going to, in the Code Lab, when you go into the link, you'll be creating a VM. You'll be installing Docker on it, because this will be run through Docker. And then you'll run the course container. So I have a container that has an initial Geth installation and the Manticore software on it. And so within this container, you're going to run Geth and Manticore. And the container also has the source code of all of the CTF levels that you'll be using. And then there are a series of Python scripts that are the solution templates for all of these levels. And these scripts have like maybe 1 or 2 pieces of things, 1 or 2 pieces of data missing, and then all you do is you fill those pieces of data in, run the script, and you'll get an exploit that you basically can send into the blockchain to get your money back. And that's for the lab, Section 5 labs. Okay, you will need to get practice using tmux and Docker, and all of these instructions are part of the Code Lab. for you to try out. Okay, and then what you're going to do is you're going to attach to tmux. Tmux is a way for you to get interactive terminals and then to detach from them without exiting it. Typically, when you SSH into a machine and you exit out of that shell that you've SSH'd into, that whole thing terminates. But what you need to be able to do is to run geth in the background and keep that interactive geth session running all the time. But you don't want to sit there and have a window logged in all the time. So tmux allows you to detach from that session and then come back in, do a tmux attach, and then to bring up that session interactively again. So that's, the code lab will walk you through how to do all of that stuff. Okay.
Is that allowed on the PSU servers?
Yeah, they have tmux on the PSU. Okay, yeah. Yeah, it depends on whether you like Control A or Control B. And that, I kid you not, there are, because Control A has specific uses in the shell, and same with Control B. And so people like, I need my Control A, so I need Control A. I don't need, I mean, I sort of need Control B, but not as badly. So that's why this is tmux. Because tmux is Control B. Yeah, screen is Control A. All right, well. That you don't need to know, but like that's why, if you really want to know why I chose tmux is that. Okay, so I want you to make sure you do that at least over the weekend, so that you'll have something running before next Monday. And with that, I'm going to take a 5-minute break and then talk about Viper.